You should already be familiar with the equation for the energy of a photon. Energy is equal to Planck's constant times the frequency of the light. This understanding was developed by Max Planck in his explanation of blackbody radiation, which is the glow of light that's emitted when a dark object is heated to high temperature. He was able to fit the frequency and intensity of the blackbody light emitted by assuming that the energy of the light was given off in quantized packets of energy, E equal to n integer values of h nu. Of course, it was assumed that the light emanating from the blackbody material came from the movement of the charged electrons. So what this means then is that if the light is being emitted by these electron oscillations in quantized packets of energies, then the electron oscillations themselves must be also quantized. The other experimental observation that's covered in your text that led to our understanding of the quantization of the hydrogen electrons was the atomic line spectrum of hydrogen, which is shown here. You know from general chemistry that hydrogen gas under an electric current emits 4 lines in the visible spectrum, and those are shown here. There's the violet line, there's a blue line here which may be difficult to see on the screen, a teal line, and then also a red line. The visible lines of hydrogen are known as the Balmer series and can be fit using the Rydberg equation. In other words, we can calculate the energies of those lines using the Rydberg equation, where NH is an integer greater than 2. We now know NH to be the upper excited quantum state for the hydrogen atom, and 2 is the second energy level, quantum energy level for the hydrogen atom, assuming a quantized energy state. So in other words, if the energy states available to the electron are quantized, as shown in this diagram, so we have specific energy levels for the transitions of the electrons, right? Red, teal, blue, and purple. And so those transitions between these fixed quantum states lead to the discrete lines in the spectrum of the hydrogen atom. If all energies, if an infinite number of energy levels were available to the electrons in the hydrogen atom, then of course you'd have many more transitions and a rainbow spectrum that was produced instead of these discrete lines. Bohr was able to later expand this understanding and fitting of the lines to take into account all of the different transitions or emissions from the hydrogen atom. In Bohr's model, R, shown here, is a constant that includes the mass, charge of the electron, and Planck's constant. And NL is the lower energy to which the electron falls, and NH is the upper excited state energy levels which the electron starts out in. So for instance, using an NL value of 1, representing the bottom, the ground state, quantum state for the electron energy, and various values of NH, 2, 3, 4, and so forth, we can calculate with this equation and the constants shown here, the energy for the lines in the Lyman series. And those are the UV lines, which are not visible by the naked eye. The bottom line here is that the line spectra of hydrogen atom are direct evidence that the energy states themselves of the electrons are quantized. The problem with the Bohr model is that he assumed that these quantized energy levels arose from the electrons being confined to circular orbits. This, of course, turned out to be incorrect. And in addition, Bohr did not provide a rationale for why the electron particle would need to be restricted to certain size orbits in the first place. Now, with the advent of de Broglie's formulation of the electron as a wave, we do find a rationale for these precise orbits, these quantized orbits. De Broglie showed that you could have a wavelength of a particle like an electron equal to Planck's constant divided by the mass of the particle times its velocity. So for instance, that of an electron. If the electron is confined to a circular orbit around the nucleus, like shown here, then that circular orbit will have a circumference of 2 pi r. In that case, if we have an electron which is behaving as a wave, it has a wavelength, in order to properly fit around that orbit, then the wavelength, right, and thus the energy of the electron, would the wavelength would have to be n integer multiples of that circumference 2 pi r in order to fit properly around the orbit. So for instance, if we have an electron with a wavelength as shown here, then n number of those wavelengths can fit around the orbit just so, and of course the wave then meets up with itself as it completes the circle. If, however, the wavelength is not an integer multiple of the circumference, then as it completes the circle, the wave doesn't meet up properly and you get destructive interference and the electron essentially decays away, which we know does not happen. So this idea of the electron behaving as a wave does in fact provide a rationale for the quantized orbits in the Bohr model, but unfortunately that doesn't save the Bohr model. The orbit idea still turned out to be problematic. Bohr couldn't extend his model to anything outside of a one-electron system, and in fact it was later shown by Heisenberg that we cannot know the position of the electron wave so precisely. In the uncertainty principle, Heisenberg demonstrated that the uncertainty in the electron position and the uncertainty in the electron's momentum, essentially energy, is greater than or equal to Planck's constant divided by 4 pi. So in other words, in order for this to work, if you want to know the electron's momentum very precisely, so that the uncertainty in the momentum is very small, right? I know it really well. In that case, the uncertainty in the position must be proportionally very, very big, and so we cannot know both the momentum in the electron and the position of the electron with a great degree of precision. What did stick, even though the idea of the orbits are out, is that the energies of the electrons are quantized, and so that still holds, and that these electrons have wave properties.